Right now, at the center of our galaxy, there is a black hole 4 million times more massive than our Sun. It has been sitting there for billions of years, consuming almost nothing, watched from a distance of 26,000 light-years by a species that only discovered it existed within the last century. For most of its history it has been quiet, patient, still. And then, on a night in May 2019, an astronomer at the Keck Observatory in Hawaii pointed a telescope toward the galactic center and watched something happen that had never been recorded before in the entire history of systematic observation. The black hole released a burst of energy so extreme that in near-infrared brightness, it briefly outshone everything around it by a factor of 75. Not twice as bright, not 10 times, 75 times brighter than its highest recorded baseline. What happened that night and what it means is what this story is about. The numbers require a moment to absorb. A flare of electromagnetic energy pouring outward from a single compact region at the center of the Milky Way, radiating at a luminosity equivalent to tens of millions of suns burning simultaneously in one place. That energy traveled 26,000 years to reach the mirrors of the Keck telescope. The astronomer watching the data stream that night was Tuan Do, an astrophysicist from the University of California, Los Angeles, leading an observing run focused on the stars that orbit close to the galactic center. He was not expecting what he saw. The brightness curve in the near-infrared band rose in a way that exceeded anything in 20 years of systematic records for this object. He looked at the data, he checked the instruments, he ran the reduction pipeline again. The signal was real, confirmed, and unlike anything seen before. Something had awakened at the center of our galaxy, and the light from that awakening had been traveling toward us since before the first human city was built. This is not a story about danger, the distance between Earth and Sagittarius. A star is so vast that no burst of energy from our galactic center can reach us with enough intensity to cause harm. This is a story about understanding, about what happens when a black hole that has spent millennia in near silence suddenly releases an event of staggering scale, about what triggers these eruptions, what the physics behind them actually looks like, and what they reveal about a region of the universe that we cannot see with our eyes, cannot reach in any physical sense, and have only begun to understand within living memory. The center of our galaxy is a place of extraordinary violence and extraordinary beauty, hidden behind layers of cosmic dust, accessible only through wavelengths of light that unaided human vision cannot perceive. What happened in May 2019 opened a new chapter in what we know about that hidden place. Tonight, we trace that chapter from its beginning. There is something quietly astonishing about the fact that human beings living on a small planet in one of the outer spiral arms of the Milky Way have managed to identify the exact location of the supermassive black hole at the galaxy's core, measure its mass to within a fraction of a percent, track individual stars orbiting it at fractions of the speed of light, and detect a single burst of energy released from a region smaller than our solar system from a distance of 26,000 light-years. The tools that made this possible did not exist a century ago. The mathematics that explains what we are observing did not exist 2 centuries ago. The concept of a black hole was dismissed as a mathematical curiosity for much of the 20th century. And yet here we are, watching the galactic center in near real time, catching events as they unfold, building a portrait of a place so alien and so remote that light from the moment of the 2019 flare left the galactic center before our species had developed writing. If you enjoy documentaries that take the universe's most extreme phenomena and reveal the science behind them in full depth, do me a small favor and hit the like button and subscribe. It genuinely helps this channel continue and lets me keep making these deep dives for you. Every subscriber makes the next video possible, and I appreciate every one of you who watches and supports this work. Now settle in, turn down the lights if you can, let the world outside go quiet. Because what we're about to explore is one of the most remote and violent places in the known universe, and the strangest part is that it is not somewhere in a distant galaxy, billions of light years away. It is at the center of our own home galaxy, 26,000 light years away, sitting in the dark and waiting for us to understand what it did. The story of Sagittarius. A star begins not with a telescope pointed at visible light, but with a young radio engineer named Carl Jansky working for Bell Telephone Laboratories in New Jersey in 1931. Jansky had been assigned the task of identifying sources of radio interference that might disrupt transatlantic telephone communications. He built a rotating directional antenna mounted on a circular track which the laboratory staff called the merry-go-round, and began systematically mapping the radio sky. He found 3 sources of interference. 2 were nearby thunderstorms, consistent with expectations. The third was a steady hiss of radio energy that peaked once every 23 hours and 56 minutes, not every 24 hours. That 4-minute difference was the decisive clue. A 24-hour period would match a source fixed relative to the Sun. A 23-hour, 56-minute period matched a source fixed relative to the stars themselves. Jansky had detected radio emission originating from somewhere beyond the solar system. When he traced the direction of maximum intensity, it pointed toward the constellation Sagittarius, toward the center of the Milky Way. Jansky published his findings in 1933, noting that the strongest cosmic radio signal came from the direction of the galactic center. The discovery attracted limited attention from professional astronomers. Radio astronomy as a discipline barely existed, and most observational astronomers worked in optical wavelengths. Compounding the challenge, the galactic center is entirely invisible in optical light due to the enormous density of dust and gas between Earth and the inner galaxy. Looking toward the galactic center in visible wavelengths produces nothing. The dust absorbs and scatters photons before they can reach us. Jansky's findings sat largely unexamined until the end of the Second World War, when the rapid development of radar technology had created an entire generation of engineers familiar with microwave and radio electronics who were seeking peacetime applications for their skills. Radio astronomy expanded dramatically in the late 1940s and 1950s, and Jansky's original galactic center signal became one of the first targets for the new generation of sensitive radio telescopes being built around the world. Through the 1950s, 1960s, and into the 1970s, radio astronomers resolved increasingly fine structure in the galactic center emission. The technology improved steadily. Larger dishes, better receivers, and eventually interferometric arrays that combined signals from multiple telescopes to achieve the resolving power of an instrument spanning kilometers allowed astronomers to pinpoint radio sources with increasing precision. The galactic center turned out to host a complex of overlapping radio sources, some diffuse and extended, others compact and intense. A particularly bright compact source sat at the dynamical center of the system, drawing interest as something potentially unusual. In 1974, using the National Radio Astronomy Observatory's baseline interferometric array, astronomers Bruce Ballick and Robert Brown made a high-resolution map of the galactic center and identified a single extremely compact non-thermal radio source at the precise center. This source was smaller than any known star-forming region and showed emission properties inconsistent with simple hot gas. It was clearly something more exotic. In 1982, Robert Brown formally proposed the name Sagittarius A for this object. The name has been used ever since. Understanding the true nature of Sagittarius. a star required a different observational strategy entirely. The compact radio source told astronomers that something energetic and small occupied the galactic center, but its exact mass and physical character could not be determined from radio data alone. The breakthrough came from tracking the individual stars that orbit extremely close to the center. In the early 1990s, two independent teams began this work. Reinhard Genzel led a team at the Max Planck Institute for Extraterrestrial Physics in Germany. Andrea Ghez led a team at the University of California, Los Angeles. Both used the world's largest optical and near-infrared telescopes equipped with an emerging technology, adaptive optic systems that compensate for atmospheric blurring by continuously reshaping the telescope mirror. The galactic center is one of the most crowded stellar environments in the galaxy, and resolving individual stars there requires angular precision that Earth's atmosphere normally prevents. Adaptive optics changed that. Suddenly it became possible to follow individual stars through positions that shifted measurably from year to year. Over the following 2 decades, both teams tracked dozens of stars in the central parsec of the galaxy, recording their positions with ever-increasing precision season after season. What the data revealed was unambiguous. The stars were not drifting randomly, they were orbiting. Some orbited at thousands of kilometers per second. One star, designated S2, was found to complete a full orbit in approximately 16 years, swinging within about 120 astronomical units of the galactic center at its closest approach and reaching a velocity of nearly 3% of the speed of light. The gravitational mass required to produce this orbit, concentrated within the volume enclosed by S2's closest approach, was approximately 4 million times the mass of our Sun. No collection of ordinary stars could be that massive and that compact. The only physically consistent explanation was a supermassive black hole. In 2020, Reinhard Genzel and Andrea Ghez were jointly awarded the Nobel Prize in Physics for this discovery, the most rigorous proof ever obtained for the existence of the supermassive object at the center of our galaxy. 4 million solar masses. The number is so large that its intuitive meaning requires unpacking. Our Sun is itself an enormous object. Its diameter is 109 times that of Earth, and more than 1 million Earth-sized planets could fit inside it. Sagittarius. A star contains the equivalent mass of 4 million such suns, compacted by gravity into a region defined by its event horizon, the mathematical boundary beyond which no information, no matter, and no light can escape. The radius of this event horizon, calculated from the Schwarzschild solution to Einstein's field equations, is approximately 12 million kilometers. In everyday terms, 12 million kilometers is enormous. Earth itself is only 12,000 kilometers across. But astronomically, 12 million kilometers is extraordinarily compact. It is smaller than the orbital radius of Mercury around our Sun, which sits roughly 58 million kilometers from the solar surface. The most massive single object in the Milky Way fits within a sphere you could place between the Sun and its innermost planet. The relationship between mass and event horizon size is one of the most counterintuitive facts in black hole physics. As a black hole becomes more massive, its event horizon radius grows proportionally. Doubling the mass doubles the Schwarzschild radius, but the average density within the event horizon decreases with the square of the mass. A stellar mass black hole of 10 solar masses has an event horizon radius of about 30 kilometers and an average density inside the horizon of trillions of kilograms per cubic meter, denser than an atomic nucleus. Sagittarius, a star with 4 million solar masses, has an event horizon with an average density of only about a few thousand kilograms per cubic meter, comparable to liquid water. The black hole at the centre of our galaxy has a lower average density within its event horizon than the ocean. This is not because the central singularity is any less extreme. It is because the event horizon has expanded to such a large scale that the interior volume has outpaced the mass. Scale dominates the physics in ways that resist ordinary intuition. Sagittarius. A star sits 26,000 light-years from Earth. This distance deserves examination. Light, travelling at nearly 300,000 kilometers per second, fast enough to circle Earth 7.5 times in a single second, takes 26,000 years to travel from the galactic centre to us. The light detected by the Keck Observatory on May 13, 2019 left Sagittarius, a star approximately 23,981 years BCE. At that moment, anatomically modern humans existed, but agriculture had not yet been developed. The last glacial maximum was only beginning to recede. The structures at Stonehenge would not be built for another 14,000 years. The entire span of recorded human history, from the first writing systems to the present, from the first cities to the current moment, all of it fits within the time that it takes for a single photon released at the galactic centre to reach a telescope on Earth. Our observations of Sagittarius. A star are, in a very literal sense, readings of deep time. The distance is also how we measure the position of Sagittarius A star. Radio astronomers use a technique called very long baseline interferometry, which simultaneously records signals from the galactic centre at radio telescopes distributed across the globe, separated by thousands of kilometres. By precisely comparing the arrival times of the same radio wavefront at different stations, this technique achieves angular resolution, equivalent to a telescope the size of the Earth's diameter. The result is a positional measurement accurate to fractions of a millisecond, good enough to track the proper motion of Sagittarius, a star itself, across the sky as the Sun and Solar System orbit the galactic centre. Combining this positional precision with the stellar orbit measurements from Keck and the Very Large Telescope gives astronomers a three-dimensional picture of the galactic centre geometry, including the precise distance to Sagittarius A star, which has been measured to an accuracy of about 1%. It is one of the most precisely known distances in the extragalactic universe. The spin of Sagittarius. A star adds another layer of complexity to understanding its environment. Astrophysical black holes are not simply defined by their mass, they also have a spin parameter, ranging from 0 for a non-rotating black hole to 1 for a maximally spinning one. A spinning black hole drags spacetime itself into rotation around it, a phenomenon called frame dragging or the lens-thirring effect. Near a rapidly spinning black hole, this frame dragging distorts the orbits of nearby plasma, tilting the innermost accretion disk into alignment with the black hole's equatorial plane, and generating additional sources of angular momentum transport and turbulence. The Event Horizon Telescope data from the 2022 imaging campaign provided constraints on Sagittarius A star's spin, suggesting it is moderate rather than extreme. This matters for understanding flares because the location of the innermost stable circular orbit depends on spin. A maximally spinning black hole allows stable orbits much closer to the event horizon, compressing the innermost emitting region into a smaller volume and potentially enabling more intense energy releases. Gravitational time dilation near Sagittarius. A star produces effects that alter the relationship between observations made from Earth and the physical events occurring at the galactic centre. General relativity predicts that clocks run slower into stronger gravitational fields. Near the innermost stable circular orbit of Sagittarius A star, time runs slower than at infinity by a factor of several, depending on the black hole's spin, the local rate of time passage is reduced to roughly 1/2 to 1/3 of the rate measured by a distant observer. This means that a flare that appears from Earth to last 1 hour actually lasted only a fraction of that time in the frame of the emitting plasma. Observed variability timescales in Sagittarius. A star's flares are therefore not directly equal to the dynamical timescales in the emitting region. They are gravitationally stretched versions of those timescales. Accounting for this gravitational time dilation is essential for correctly interpreting what the observed light curves tell us about the physical size and speed of the emitting region. The temperature of the plasma in the immediate vicinity of Sagittarius A star during a major flare reaches extraordinary values. Theoretical models of magnetic reconnection events near the innermost stable circular orbit, calibrated against the observed near-infrared and X-ray brightness ratios during flares, consistently predict electron temperatures exceeding 1 billion degrees Kelvin at the peak of reconnection activity. For context, the centre of the Sun reaches temperatures of roughly 15 million degrees Kelvin. A major Sagittarius A star flare generates electron temperatures roughly 60 times hotter than the solar core, in a volume that would fit within the orbit of Saturn. At these temperatures, the electrons are moving at velocities so close to the speed of light that their inertia is multiplied by relativistic factors of several. Their effective mass is several times their rest mass, which dramatically changes how they interact with magnetic fields and how efficiently they radiate. The radiation from such a plasma is characteristic of what physicists call a relativistic synchrotron source, a source that cannot be produced by any physical process operating at lower energies. For most of its observable history, Sagittarius A star has been what astronomers call quiescent, quiet. It is emphatically not an active galactic nucleus. Active galactic nuclei, found in galaxies across the observable universe, are powered by supermassive black holes consuming enormous quantities of material and converting a significant fraction of its rest mass energy into radiation. They can outshine every star in their host galaxy combined. Quasars, blazars, Seyfert galaxies and radio galaxies are all manifestations of this process at different masses, orientations, and accretion rates. Sagittarius. A star, by contrast, radiates at a level roughly 10 billion times lower than the theoretical maximum for a black hole of its mass accreting at full efficiency. This places it firmly in the category of low-luminosity active galactic nuclei, a class of objects that have supermassive black holes at their centres, but whose current accretion rates are too low to produce dramatic activity. Our galactic centre is, by cosmic standards, exceptionally calm. The physical reason for this underluminosity relates to how material reaches the black hole. In the most luminous active galactic nuclei, gas from the host galaxy is efficiently channeled into a dense, thin accretion disk that spirals tightly inward, converting up to 40% of the infalling mass into radiation before it reaches the event horizon. In Sagittarius A star, the accretion proceeds through what theorists call an advection-dominated accretion flow. In this regime, the gas falling toward the black hole is hot and tenuous rather than cool and dense. Instead of radiating its energy efficiently, the hot gas carries most of that energy with it as it falls in. Much of it is also expelled outward in thermally driven winds before reaching the event horizon. The accretion rate is estimated at roughly 10 to the power of -9 solar masses per year, approximately 1 Earth mass of material consumed every million years. For a 4 million solar mass black hole, this is a starvation ration. It explains why Sagittarius A star has the mass of a monster and the luminosity of a candle. Even in its quiet state, Sagittarius A star is not completely still. The object exhibits measurable variability on timescales ranging from minutes to hours, primarily detected in near-infrared and X-ray wavelengths. Astronomers monitoring the galactic center have catalogued dozens of what they call flares, transient brightenings in which the luminosity of the galactic center source rises sharply above its baseline and then subsides. These flares do not arise from new material falling in from large distances. They originate in the immediate environment of the black hole, within a region just a few times the event horizon radius, where magnetic field dynamics and plasma physics periodically generate sudden, intense releases of energy. On a typical observing night, Sagittarius A produces a handful of small near-infrared fluctuations and one or two moderate X-ray brightenings. They last anywhere from minutes to a couple of hours. They brighten the source by factors of 2 to 10. They are common, routine, and expected until they are not. The statistical character of Sagittarius A's normal flaring was established over 2 decades of systematic monitoring. Astronomers analysed the distribution of flare amplitudes, durations, and waiting times between flares and found that the system followed a pattern consistent with self-organised criticality, the same mathematical framework that describes earthquakes, solar flares, and avalanches. Small events are far more frequent than large ones. The relationship between flare size and frequency follows a power law. For every 10-fold increase in flare brightness, the number of such flares decreases by a specific factor. This means that a flare 75 times brighter than typical is expected to be extraordinarily rare, perhaps once per decade or less in the most generous statistical extrapolations from the historical data. Whether the May 2019 event falls within the tail of this power law distribution, or represents a fundamentally different category of event driven by specific triggering conditions, is one of the central unresolved questions that emerge from its detection. In 2012, the Chandra X-ray Observatory captured the brightest X-ray flare from Sagittarius A then on record, reaching a luminosity approximately 400 times the quiescent X-ray baseline, a factor 10 times the typical bright flare. This event, analysed in a paper led by Gabriele Ponti and colleagues and published in 2015, stood as the record holder for X-ray flare amplitude until the systematic analysis of the 2019 data revealed the near-infrared mega flare. The 2012 X-ray flare lasted roughly 2 hours, consistent with an emitting region of the size expected near the innermost stable circular orbit. Its spectral properties were consistent with synchrotron self-Compton emission from a population of electrons heated to temperatures exceeding 100 million electron volts. Notably, the 2012 event was detected in X-ray wavelengths, but had no confirmed near-infrared counterpart at comparable amplitude, illustrating that near-infrared and X-ray flares, while often correlated, can in some cases occur with very different relative amplitudes, suggesting that the electron energy distribution during different events may vary significantly from flare to flare. Near-infrared and X-ray flares from Sagittarius. A star show statistical correlation but not perfect synchrony. Studies combining Chandra X-ray data with near-infrared data from Keck and the Very Large Telescope have established that bright X-ray flares are almost always accompanied by near-infrared brightenings. But the reverse is not always true. Some bright near-infrared flares have no detectable X-ray counterpart. This asymmetry provides important information about the physical mechanism. If near-infrared emission arises from electrons at relatively modest energies spiraling in magnetic fields, while X-ray emission requires either much more energetic electrons or a second upscattering process, then flares producing only moderate electron acceleration might produce visible near-infrared brightening without reaching the energy threshold required for significant X-ray emission. Only the most extreme acceleration events, those producing the highest energy electron populations, manifest across both wavelength bands simultaneously. The May 2019 megaflare, observed to have an X-ray counterpart consistent with its exceptional near-infrared amplitude, was clearly one of these high-energy events. Polarization measurements of the near-infrared emission during flares have provided direct evidence for the synchrotron origin of the radiation. Synchrotron radiation is intrinsically linearly polarized perpendicular to the magnetic field in which the electrons are spiraling. If the magnetic field in the emitting region is ordered, pointing predominantly in one direction, the synchrotron radiation will be measurably linearly polarized when viewed from Earth. Observations of Sagittarius A star during near-infrared flares have detected linear polarization at levels of up to 30%, with the polarization angle rotating during the course of the flare. The rotation of the polarization angle is consistent with the emitting hotspot orbiting the black hole as proposed from the gravity orbital motion measurements, with the magnetic field orientation changing as seen from Earth as the hotspot moves around its orbit. These polarization measurements provide one of the strongest observational links between the theoretical model, a magnetically reconnection-powered synchrotron-emitting hotspot in near-circular orbit near the innermost stable circular orbit, and the observational data. The X-ray flares from Sagittarius A star were first definitively observed by NASA's Chandra X-ray Observatory shortly after its launch in 1999. Chandra's angular resolution, the finest of any X-ray telescope ever built, is good enough to isolate the emission from the compact galactic center source against the dense surrounding field. In 2001, a team led by Frederick Baganoff at the Massachusetts Institute of Technology reported the detection of a strong X-ray flare from Sagittarius A star, lasting roughly 10,000 seconds and reaching a peak luminosity approximately 45 times the baseline X-ray brightness. This was the first clear evidence that the galactic center black hole produced dramatic transient events. The announcement stimulated the formation of coordinated monitoring programs specifically designed to catch future flares across multiple wavelengths simultaneously, with the goal of understanding the physical mechanism behind them. Chandra has since accumulated millions of seconds of galactic center observing time, building a statistical archive that forms the backbone of our knowledge of Sagittarius A star's X-ray behavior. The near-infrared monitoring campaign, conducted primarily with the Keck Observatory and the Very Large Telescope in Chile, has run in parallel with the X-ray program since the mid-1990s. Near-infrared light penetrates the galactic dust far more effectively than optical light, and the near-infrared cameras on both facilities, combined with adaptive optics, have produced extraordinary records of the galactic center's behavior. In the near-infrared, Sagittarius A star fluctuates continuously rather than sitting at a steady level. There is an underlying stochastic variability superimposed with more distinct flare events. The statistical analysis of these variations has been the subject of dozens of published studies attempting to characterize the underlying physical process, its variability timescales, and its amplitude distribution. The statistical findings mirror those in X-ray, a power law distribution of event amplitudes, with large events becoming exponentially rarer as their brightness increases. This established the expectation, violated dramatically in May 2019, that very large near-infrared flares should be extraordinarily uncommon events in the observational record. Before the events of May 2019, astronomers had reason to watch Sagittarius A star with particular attention. In May 2018, the star designated S2 completed its closest approach to the black hole, an event called periapsis, reaching a distance of only about 120 astronomical units and a velocity of approximately 7,600 kilometers per second, roughly 2.5% of the speed of light. S2 is a massive, hot blue star, roughly 15 to 20 times the mass of our Sun. At periapsis, it passes close enough to Sagittarius A star that tidal forces and the interaction between the star's outflowing stellar wind and the black hole's gravitational field can, in principle, divert some fraction of the wind material toward the accretion region. The 2018 periapsis had been anticipated for years and monitored with every available instrument. The gravity instrument at the Very Large Telescope captured the periapsis passage in extraordinary detail, providing the most precise measurement ever made of stellar orbits around a black hole, and directly detecting the relativistic precession of S2's orbit predicted by general relativity. The gravity instrument is itself worth understanding. It is an optical interferometer that combines the light from all 4 8-meter unit telescopes of the Very Large Telescope array into a single coherent beam, effectively creating a telescope with a resolving power equivalent to a mirror 130 meters across. The angular resolution this achieves is measured in microarcseconds, millionths of an arcsecond. At the distance of the galactic center, 1 microarcsecond corresponds to a physical scale of roughly 120 astronomical units. Gravity can therefore resolve structures in the galactic center region that are smaller than the orbit of Neptune around our Sun, measured from 26,000 light-years away. This precision is what allowed gravity to track S2's position through the 2018 periapsis with sufficient accuracy to detect the Schwarzschild precession of the orbit, the advance of the orbital periapsis predicted by general relativity, observed here not for a planet around the Sun as with Mercury, but for a star around a supermassive black hole. There was a second reason for heightened anticipation. In 2013 and 2014, a diffuse cloud of gas and dust designated G2 had made its own close passage around Sagittarius A star, coming within roughly 2,000 Schwarzschild radii of the event horizon. Predictions before the encounter varied dramatically. Some models suggested G2 was a compact stellar core surrounded by a gaseous envelope. Others suggested it was a purely gaseous clump that would be tidally shredded and consumed. The actual encounter produced observable deformation of G2's structure, but no immediately spectacular flaring response. The debate over G2's nature was not resolved. What was established is that G2's passage left disrupted material in the galactic center region that would continue to spiral inward over years. By 2018 and 2019, some fraction of the material disrupted from G2 might finally be reaching the innermost accretion zone near the event horizon. Both S2's periapsis and the G2 aftermath had primed the galactic center as a particularly interesting observing target heading into 2019. Twando arrived at the Keck Observatory in the spring of 2019 to carry out systematic monitoring of the galactic center. The observations used the NIRC 2 camera on the Keck 2 telescope, fed through the facility's adaptive optics system. The laser guide star adaptive optics at Keck works by firing a powerful laser beam into the upper atmosphere at an altitude of roughly 90 kilometers, exciting a layer of sodium atoms that glows as an artificial star. The adaptive optics computer measures the blurring of this artificial star caused by atmospheric turbulence and corrects for it by deforming the primary telescope mirror using an array of small actuators that reshape the mirror surface hundreds of times per second. The result is angular resolution close to the theoretical diffraction limit of the 10-meter Keck mirror, sharp enough to separate individual stars in the dense central cluster around Sagittarius. A star that appear, at 26,000 light-years, separated by tiny fractions of a single arcsecond. The setup was the same as on dozens of previous observing runs. The night of May 13, 2019, was expected to produce the same kind of routine data. The data stream on May 13th did not look routine. As Du and his team watched the near-infrared brightness of the galactic center source in the K-band, centered at a wavelength of about 2 micrometers, the signal began rising. It kept rising past the level of the most active previously recorded near-infrared flares. It continued past the previous record by a large margin. The team's first instinct was instrumental skepticism. Could a cosmic ray have struck the detector? Was there an artifact in the reduction pipeline? Was the adaptive optics correction producing a spurious concentration of light? Each of these possibilities was checked systematically and eliminated. The rising brightness was real. It would appear inconsistently across multiple independent analysis paths. The source at the galactic center was genuinely dramatically brighter than it had ever appeared in 20-plus years of systematic near-infrared monitoring. Du later described looking at the data on that first night and not quite believing what he was seeing, and then checking everything again and still believing it. The peak brightness reached during the May 2019 event was approximately 75 times higher than the median near-infrared brightness of Sagittarius A star, relative to the typical bright state flux established from the multi-year monitoring baseline. The previous record brightening in the near-infrared, from all available observations going back to the late 1990s, was a factor of roughly 10 to 20 above the typical bright state level. The 2019 event exceeded that record by more than threefold. In the history of near-infrared galactic center astronomy, nothing comparable had been documented. The data had to be carefully verified, checked for instrumental artifacts, and confirmed against multiple independent reduction methods. The April through September 2019 observing season as a whole, not just the single night of May 13th, showed near-infrared flux levels systematically elevated above the historical average. This broader seasonal pattern suggested that May 13th was the extreme manifestation of a sustained period of enhanced activity rather than an isolated single spike in an otherwise normal year. The phrase brighter than 10 million suns requires careful context because it describes a real physical quantity. During the May 2019 flare, the near-infrared luminosity of Sagittarius. A star in the K-band reached a level that, when combined with standard assumptions about the source's broadband spectral energy distribution during active states, corresponds to a total electromagnetic luminosity of approximately 10 to the 36th to 10 to the 37th ergs per second. The Sun radiates at about 4 times 10 to the 33rd ergs per second. The ratio at the peak of the flare amounts to thousands to tens of thousands of solar luminosities in the near-infrared band alone. Across all observed wavelengths simultaneously, near-infrared, mid-infrared, X-ray, the integrated luminosity during the most intense phase approaches or exceeds 10 to the 37th ergs per second, equivalent to the combined output of 10 million or more Sun-like stars. The title is not rhetorical. It is an order of magnitude characterization of a real measurement of electromagnetic energy. Twando and his team submitted their findings to the Astrophysical Journal Letters in July 2019, and the paper was published in August under the title Unprecedented Near-Infrared Brightness and Variability of Sagittarius A star. The paper presented not just the May 13th peak, but the full 2019 observing dataset, showing that on every night of the 2019 monitoring run analysed for the paper, the near-infrared brightness of Sagittarius A star exceeded the brightest flux levels seen in comparable observations from any previous year. The systematic elevation across the entire observing window distinguished the 2019 event from a simple one-time spike. The paper was careful about interpretation. Du and his colleagues noted the correlation with the S2 periapsis and the G2 aftermath as plausible contributing factors, but explicitly acknowledged that the available evidence did not allow a definitive attribution to either. The standard of scientific caution prevailed. The measurement was described precisely and completely. The physical interpretation was presented as hypotheses to be tested by future observations rather than conclusions already established. Simultaneous and near-simultaneous observations in X-ray wavelengths provided additional context for interpreting the near-infrared megaflare. The Chandra X-ray Observatory, the European Space Agency's XMM Newton satellite, and NASA's Neil Gehrels Swift Observatory each collected data from the galactic center region during the 2019 observing season. The X-ray data showed an elevated rate and amplitude of flaring activity throughout the season, consistent with the enhanced near-infrared behavior. Although scheduling constraints prevented a direct X-ray measurement at the exact moment of the May 13th peak, what the X-ray record did establish was a pattern of frequent, moderately bright X-ray events across the 2019 window at a rate and amplitude higher than the long-term historical average. The coordinated multi-wavelength portrait was coherent. Sagittarius A star had entered a state of substantially elevated activity in 2019, not just a momentary spike, but a sustained period of enhanced near-infrared and X-ray output, with May 13th representing its most extreme observed manifestation. When Sagittarius A star is not flaring during what astronomers call the quiescent or dark state, it is almost invisible at near-infrared wavelengths. The near-infrared emission from the galactic center source in its lowest state is so faint that it is difficult to distinguish from the combined light of the dense cluster of stars surrounding it. This presents a practical observational challenge: to measure the true quiescent brightness of Sagittarius. A star astronomers must carefully subtract the contributions of every nearby star from the measured light in the central pixel, which requires knowledge of each star's brightness, position, and point spread function. The faintness of Sagittarius. A star in its quiet state is itself informative. It tells us that the accretion rate is so low and the emission mechanism so radiatively inefficient that even the thermal emission from the innermost accretion flow falls below the sensitivity of current near-infrared instruments during periods of minimal magnetic activity. The flares are, in a sense, the only times we can actually see Sagittarius A star directly in the near-infrared. The sub-millimeter emission from Sagittarius A star provides a window into the accretion flow at intermediate scales between the near-infrared emitting zone during flares and the much larger radio-emitting region. At wavelengths of around 1 mm, the emission traces warm plasma at radii of tens to hundreds of Schwarzschild radii from the black hole, further out than the innermost stable circular orbit but much closer than the large-scale accretion flow. This sub-millimeter emission is less variable than the near-infrared during flares, but it does respond with a delay of roughly 20 to 60 minutes after the near-infrared flare peaks, consistent with the time for the energy deposited by the magnetic reconnection event to propagate outward from the innermost region into the broader plasma distribution. This outward propagation of the flare signature across wavelengths, from near-infrared and X-ray peaks first, followed by sub-millimeter delays, then radio delays of hours, provides a direct observational signature of the physical evolution of the flare plasma as it cools and expands away from the compact emitting region. The physics that generates these flares centers on the behavior of magnetized plasma in the innermost region of the black hole's accretion flow. The leading mechanism is magnetic reconnection. In a plasma, a gas of ions and free electrons, magnetic field lines are effectively frozen into the conducting gas and advected with it as the gas flows. When infalling plasma from different directions meets near the event horizon, it can bring oppositely directed magnetic field lines into contact. In a perfectly conducting plasma, these opposing field lines cannot simply cancel. Instead, under the right conditions, they tear apart and reconnect in new configurations through a thin current sheet. This reconnection event releases the stored magnetic field energy explosively, converting it into heat and accelerating charged particles, primarily electrons, to high relativistic energies in a very short time. Magnetic reconnection is the same fundamental process that drives solar flares on our own sun. Near Sagittarius, a star, the magnetic fields are far more intense, the plasma temperatures are far higher, and the gravitational field itself participates actively in the dynamics. Near a black hole, the innermost region of stable orbital motion is called the innermost stable circular orbit, abbreviated ISCO. This is the closest distance at which a particle can maintain a stable orbit around the black hole without spiraling inevitably inward toward the event horizon. For a non-rotating black hole of Sagittarius A star's mass, the ISCO lies at a radius of approximately 36 million kilometers, 3 times the Schwarzschild radius. Gas and plasma circulating at this radius moves at a substantial fraction of the speed of light. The magnetic fields threading this gas are enormously compressed by the converging orbital dynamics and tangled by differential rotation. This environment is ideal for magnetic reconnection events of extraordinary intensity. When reconnection occurs at or near the ISCO, the energy release can be rapid and overwhelming, producing the kind of sudden luminosity spike observed on May 13, 2019. The entire volume responsible for the flare, the hotspot of enhanced emission, is smaller than the distance from Earth to the Sun. It is the most compact energetic event we can observe from our position in the galaxy. The electrons accelerated by magnetic reconnection near the ISCO radiate their energy through synchrotron emission. When a relativistic electron moves through a magnetic field, the magnetic force curves its path, causing it to spiral along field lines while radiating photons. The frequency of emitted photons depends on the electron's energy and the magnetic field's strength. Electrons accelerated to high energies by magnetic reconnection in the strong magnetic fields near a supermassive black hole naturally produce photons in the near-infrared and X-ray portions of the spectrum. The near-infrared emission traces electrons at the lower end of the accelerated energy distribution. The X-ray emission arises either from the most energetically extreme electrons in the same population or from a process called synchrotron self-Compton scattering, in which a near-infrared photon collides with a relativistic electron and is boosted to X-ray energies through the transfer of kinetic energy from the fast-moving particle to the photon. Both processes produce the characteristic multi-wavelength flare signature that has been observed repeatedly from Sagittarius A star, and both are consistent with the elevated emission seen across wavelengths in 2019. The duration of individual flares constrains the physical size of the emitting region through the light-crossing time argument. Because no information propagates faster than light, a source can only vary coherently over a timescale equal to or longer than the time it takes light to cross the emitting region. A flare that rises and falls in 60 minutes must originate in a region no larger than 60 light minutes across, about 10 times the Earth-Sun distance. Flares from Sagittarius. A star typically have rise and fall timescales between 10 minutes and 2 hours, constraining the emitting volume to scales of tens to a few hundred Schwarzschild radii. This is a physically tiny region. At the temperature required to produce the observed X-ray emission through synchrotron or Compton processes, the plasma in this region must reach temperatures exceeding 1 billion degrees. Kelvin, temperatures comparable to those in the cores of the most massive stars, but confined to a region small enough to fit within the orbit of Saturn around the Sun. The magnetic field strength near Sagittarius. A star has been estimated from the flare properties and from theoretical modelling of the accretion flow. The values converge on field strengths of between roughly 10 and 100 Gauss in the innermost accretion region, the area within a few Schwarzschild radii of the event horizon. For reference, Earth's surface field is half a Gauss, and sunspot fields reach a few thousand Gauss, the field near Sagittarius. A star is intense but not unprecedented. What makes it physically extraordinary is its combination with extreme plasma density, extreme temperature, and the curvature of spacetime in the regime of strong gravity. In the innermost stable orbit region, general relativistic effects are not small corrections to Newtonian physics, they are dominant. The frame-dragging effect of the black hole's spin distorts the orbit of nearby plasma. Gravitational time dilation significantly alters the relationship between locally measured time and the time recorded by the distant observers. Magnetic reconnection events in this environment are embedded in a physical regime, with no parallel elsewhere in the observable universe reachable by current probes. One of the most remarkable aspects of the 2019 flare is the temporal relationship between the event and its detection. The photons caught by the Keck mirror on May 13, 2019, left Sagittarius A star approximately 23,981 years earlier. The magnetic reconnection event that produced them, the sudden energy release, the acceleration of electrons to relativistic speeds, all of this happened while glaciers still covered large portions of the northern hemisphere, and anatomically modern humans were living in small migratory groups on a very different Earth. The photons travelled for the entire span of recorded human civilization, plus all of prehistory going back to before the invention of pottery, before finally being intercepted by the instruments on a volcano in Hawaii. This is one of the quietest and most profound facts in astronomy. Every observation of the galactic centre is an observation of the past, a reading of events that have long since ended, their light still travelling toward any observer patient enough to wait in the right place. The question of what triggered the extraordinary 2019 event leads back to S2 and its 2018 periapsis. At periapsis, S2 moved at roughly 7,600 km per second, about 2.5% of the speed of light, while passing approximately 120 astronomical units from Sagittarius A star. At this distance and velocity, the tidal forces from the black hole interact with S2's stellar wind. Massive hot stars like S2 continuously expel material from their surfaces in fast, dense stellar winds. Near periapsis, some fraction of this wind is captured by Sagittarius A star's gravity, rather than streaming freely into interstellar space. The captured material does not fall immediately to the event horizon. It must first circulate in the accretion zone, gradually losing angular momentum through interactions with the existing plasma and magnetic field, before spiralling inward toward the ISCO. The timescale for this inward drift is estimated at months to roughly a year. A fresh injection of wind material from S2's periapsis in May 2018 could plausibly trigger enhanced accretion activity in the innermost region by approximately May 2019, exactly when the megaflare was observed. The timing match between S2's 2018 periapsis and the 2019 megaflare, a gap of approximately 12 months, is consistent with theoretical predictions, but cannot by itself prove causation. Sagittarius. A star's accretion rate fluctuates for many reasons, and a particularly large flare might have occurred in 2019, even without any fresh material input from S2. To test the S2 hypothesis more definitively, astronomers look for patterns. Does the flaring rate increase systematically in the months following S2 periapsis passages and then decline? Does the timing of enhanced activity across multiple orbital cycles of S2 show a consistent lag relative to periapsis? S2 completes one orbit in roughly 16 years, providing only a few opportunities per human observational campaign to check this pattern. The 2018 periapsis is only the second one to occur during the modern systematic monitoring era. Comparing the galactic center's behavior in the year following the 2002 periapsis with its behavior in the year following the 2018 periapsis is one of the empirical tests available, and researchers are currently conducting exactly this comparison with the available archival data. The G2 cloud alternative presents its own complexities. G2 was identified in 2011 as a compact reddish source moving towards Sagittarius A star on an orbit would bring it to a closest approach of only a few thousand Schwarzschild radii, extraordinarily close. The astronomical community prepared for G2's periapsis in 2014 with extensive monitoring campaigns, some expecting a dramatic disruption event in which the cloud would be tidally shredded and consumed, producing an observable brightening. The reality was more ambiguous. G2 survived its encounter without the spectacular disruption some models had predicted, suggesting it was not a purely gaseous cloud but likely a compact object, possibly a binary star merger product surrounded by a dusty gas envelope. The passage did visibly deform G2's shape, stretching it along the orbit and dispersing some of its outer envelope. The dispersed material has been drifting inward since 2014, and by 2018 to 2019, some of that material could reasonably have reached the innermost accretion region. The timing is consistent with G2 contributing to the enhanced 2019 activity, but the contribution cannot be isolated from the S2 effect or from intrinsic accretion variability. The broader family of G objects discovered in the years following G2's identification adds another dimension to this picture. At least 5 additional objects with properties similar to G2 have been found in the galactic center region, each following an orbit that will eventually bring it to a close passage with Sagittarius A star. The current evidence favors interpreting these objects as binary stellar mergers, close binary pairs whose orbits have decayed through gravitational interactions in the dense galactic center environment until the two stars merged into a single, inflated, dust-enshrouded object. If this interpretation is correct, binary mergers in the galactic center may be relatively common, periodically delivering bloated, gas-rich stellar objects to close orbits around Sagittarius A star, where they can deposit material into the accretion zone. The G object population may represent an ongoing, slowly replenished supply of triggers for enhanced accretion episodes. The 2019 megaflare may have been the result of one such delivery, or it may reflect the cumulative effect of multiple deliveries arriving in the same narrow time window. The gravity instrument has produced some of the most striking direct evidence for what happens near Sagittarius A star during flares. In observations collected during 2018 and 2019, gravity detected near-infrared flares and simultaneously measured the position of the emitting source with micro-arc-second precision. During flares, the centroid of the near-infrared emission was found to move, not randomly but in a coherent pattern, tracing what appeared to be a circular arc around the nominal position of Sagittarius A star. The radius of this arc corresponded to approximately 5 times the event horizon radius, and the orbital period of the motion was about 45 minutes. This period is consistent with the Keplerian orbital period at that radius around a 4 million solar mass black hole, accounting for the time dilation expected at that proximity to the event horizon. The interpretation is a hotspot, a localized region of enhanced plasma emission, orbiting Sagittarius, a star near the innermost stable circular orbit, completing a full circuit in the time it takes a person to take a lunch break, while situated 26,000 light-years away. The Atacama Large Millimeter Array provided complementary observations at submillimeter wavelengths, probing a slightly different physical region than the near-infrared observations. Millimeter and sub-millimeter emission from Sagittarius A star arises from somewhat larger radii than the near-infrared emitting zone during flares, and traces electrons at the lower end of the energy distribution as they cool after the peak of reconnection activity. LMA's high sensitivity allowed it to track the evolution of flaring emission in time, catching the post-peak cooling phase of flare events in detail. The cooling timescale measured from the millimeter light curves is consistent with the cooling rate expected for synchrotron emitting electrons losing energy to radiation in a magnetic field of about 10 to 100 Gauss, providing an independent confirmation of the magnetic field strength estimates derived from modeling the near-infrared and X-ray data. The multi-wavelength picture assembled from gravity, ALMA, Keck, and the X-ray facilities during the 2019 epoch represents the most complete portrait of an enhanced Sagittarius A star activity period ever assembled. The Event Horizon Telescope, the global array of radio observatories that in 2019 produced the first image of a black hole's shadow, the 6.5 billion solar mass black hole in the Messier 87 galaxy, also targeted Sagittarius A star. Unlike M87 star, which is enormous and 55 million light-years away, Sagittarius A star is close but much smaller. Both subtend roughly similar angular sizes on the sky, making Sagittarius A star an equally compelling target for direct imaging at radio wavelengths. The challenge is that Sagittarius A star varies on timescales of minutes, much faster than the hours-long integration required to build up enough data for an image, making it far harder to image than the steadier M87 star. The Event Horizon Telescope collaboration successfully produced the first image of Sagittarius A star's shadow in 2022, published in 6 simultaneous papers in the astrophysical journal Letters. The image showed a bright, blurry ring of radio emission surrounding a darker central shadow, consistent with a 4 million solar mass black hole at 26,000 light-years distance. It was direct visual confirmation of what stellar orbits had already proven gravitationally. The 2022 image of Sagittarius A star's shadow deserves attention beyond its historical significance as a visual confirmation. The shape and properties of the bright ring provide direct tests of general relativity in the strong gravity regime. In general relativity, light passing close to a black hole is bent by the gravitational field. Photons on certain trajectories orbit the black hole multiple times before escaping outward. This creates a characteristic ring of enhanced brightness surrounding the dark shadow, with a diameter that depends on the black hole's mass and spin. The Event Horizon Telescope measured this ring size at approximately 50 microarcseconds, consistent with a 4 million solar mass black hole at the galactic center distance. The shape of the ring and the relative brightness of different portions of it constrain the black hole's spin parameter and the geometry of the emitting plasma. The data are consistent with Sagittarius A star having a moderate spin, not maximally rotating but not stationary either. This spin carries implications for the energy available in the innermost accretion zone and for the mechanism of any jet formation. While Sagittarius A star lacks an obvious powerful relativistic jet of the kind seen in active galaxies like M87, there is evidence for mild outflow from the galactic center region. Radio observations have detected elongated, mildly non-thermal emission near Sagittarius A star on scales of a few hundred to a few thousand Schwarzschild radii, The emission is consistent with the sub-relativistic collimated outflow, a weak jet, carrying energy away from the innermost accretion region at velocities that are a significant fraction of the speed of light but far below the near light speed bulk motion seen in the most powerful active galactic nuclei. The existence of even a mild jet from Sagittarius A star is theoretically significant because it implies that some fraction of the gravitational energy tapped by accreting material is converted not into radiation but into mechanical energy, the kinetic energy of outflowing plasma. This jet power, if sustained over millions of years, could contribute to the energetics of the Fermi bubbles, and during flare events, the conditions near the innermost stable circular orbit may transiently approach those needed to launch brief episodes of enhanced, more collimated outflow. Understanding the broader context of the 2019 mega flare requires comparing Sagittarius A star with other galactic nuclei that are similarly underluminous. Astronomers have identified dozens of low-luminosity active galactic nuclei in nearby galaxies whose central black holes show properties qualitatively similar to Sagittarius A star, low accretion rates, advection-dominated flows, occasional flaring activity. The nearest external example is the nucleus of the Andromeda galaxy, Messier 31, whose central black hole has a mass of roughly 100 million solar masses, about 25 times more massive than Sagittarius A star, but is similarly underluminous for its mass. The Andromeda nucleus shows radio and X-ray variability suggestive of occasional enhanced accretion episodes, though at much lower absolute luminosity than even Sagittarius A star because of its larger distance. Studying these nearby analogues provides a broader context for understanding whether the behavior observed at the galactic center is common or unusual among black holes of similar mass and accretion regime, and whether the 2019 megaflare represents a universal feature of these systems or something specific to the Milky Way's galactic center environment, the physical environment of the innermost parsec around Sagittarius. A star is unlike anything else in the accessible universe. Within the central light year, the stellar density exceeds 1 million stars per cubic parsec, more than 1 million times denser than the solar neighborhood. The velocity dispersion of these stars reaches several hundred kilometers per second. Star-star collisions, while still rare in absolute terms, are enormously more common than anywhere in the outer galaxy. Stellar winds from the dozens of massive O and B stars in the region continuously fill the galactic center volume with hot, fast-flowing plasma that serves as the reservoir from which Sagittarius A star feeds. This hot wind plasma, with temperatures of tens of millions of degrees and outflow velocities of several thousand kilometers per second, creates a complex, turbulent environment in which the accretion of material onto the black hole is regulated not simply by gravity, but by the thermodynamics and dynamics of the hot wind. The 2019 megaflare occurred within this environment, triggered by whatever configuration of orbits and winds happens to channel an unusually large pulse of material toward the innermost accretion zone at that particular time. Understanding what the 2019 megaflare tells us about Sagittarius. A star's activity requires placing it in the context of the galactic center's longer history. The fluorescent molecular clouds around the galactic center provide one window into that history. Dense molecular clouds, when illuminated by intense X-ray radiation, absorb those X-rays and re-emit them at characteristic energies. The clouds glow in X-rays as echoes of whatever illuminated them. Several large molecular clouds near the galactic center, including the complex known as Sagittarius B2, show exactly this X-ray fluorescence. But the current Sagittarius A star is far too dim to illuminate those clouds to the observed brightness. To explain the observed fluorescence, astronomers calculate that Sagittarius A star must have been approximately 300 to 1,000 times brighter than it is today, sometime between 100 and 400 years ago, before modern astronomy. This echo preserved in gas clouds that absorbed and re-emitted X-rays from a past flare shows that even within a few centuries, Sagittarius A star has produced events far more intense than any currently observed. The Fermi bubbles represent evidence of activity at a far greater scale than the echo in molecular clouds. In 2010, analysis of data from the Fermi Gamma Ray Space Telescope revealed two enormous lobes of high-energy emission extending north and south from the galactic center, each spanning approximately 25,000 light-years in height, as tall as the entire Milky Way disk is wide. The boundaries of these structures are sharp, consistent with supersonic shock fronts driven by an energetic outflow. The gamma-ray emission within the bubbles has a hard spectrum inconsistent with ordinary stellar processes. The total energy required to produce the Fermi bubbles is estimated at roughly 10 to the 57th ergs. One leading explanation attributes the bubbles to a period several million years ago, when Sagittarius A star was accreting at a rate millions of times higher than today, driving jets of relativistic particles into the galactic halo. If this is correct, the black hole that sits quietly at the galactic center today was, within the span of human evolutionary history, something that would be classified as a low-luminosity active galactic nucleus in any other galaxy we observe. The 2019 megaflare, while extraordinary by the standards of the modern observational record, exists within this context of episodic activity spanning millions of years. The sustained quiet of recent decades may itself be anomalous in Sagittarius A star's longer history. What is clear is that the black hole's feeding rate is not fixed. It responds to the material in its environment. It brightens when fresh material reaches the innermost accretion zone. It flares dramatically when that material is disturbed by the passage of nearby stars or clouds. And it has, in the relatively recent past by geological standards, sustained feeding episodes of a scale that dwarfs anything we have observed in the modern era. The 2019 event sits at the high end of contemporary observations, but at the low end of what the galactic center has produced across its full documented history. This puts the excitement of May 13, 2019 in a sobering perspective. It was not the most energetic event Sagittarius A star has ever produced. It was simply the most energetic one we happened to be watching when it occurred. After the 2019 observations were published, the Global Galactic Center research community organized an intensified monitoring response. Proposals were submitted to every major observatory with galactic center access: Chandra, XMEM Newton, Swift ALMA, the Very Large Telescope Keck, and the Spitzer Space Telescope during its final operational months. Dedicated observing programs were approved that dramatically increased the cadence of monitoring compared to the pre-2019 baseline. The goal was twofold. First, to catch any subsequent large flares as they occurred, rather than discovering them in archival data. Second, to characterize the statistical behavior of the galactic center in the period following the megaflare, providing the most complete picture yet of how elevated activity states evolve over months and years. The coordinated response itself was a demonstration of how modern astrophysics operates. A surprising discovery triggers a rapid, community-wide mobilization that pools resources across institutions and international boundaries to address the most pressing questions as efficiently as possible. The monitoring campaigns that followed the 2019 megaflare found that the galactic center remained somewhat more active than the pre-2019 historical average through 2020 and into subsequent years, though no event matching the May 13th peak was detected. The near-infrared brightness distribution in 2020 and 2021 showed higher average flux levels than the long-term historical baseline established from the 1990s through 2018, consistent with an elevated activity state that was gradually subsiding rather than immediately returning to the pre-2019 quieter level. This gradual decline is consistent with the idea that a finite supply of fresh material from S2's stellar wind, from G2 remnants from some other source, reached the innermost accretion zone in 2019 and has been progressively consumed, with the activity returning to quiescence as that extra supply is depleted. The longer the elevated activity persists and the more data that accumulate, the more constrained the theoretical models of what happened become. The stellar dynamics of the galactic center virtually guarantee future enhanced activity episodes. S2 will return to periapsis in approximately 2034 and again in approximately 2050, providing 2 more opportunities within this century to test the hypothesis that S2 periapsis passages enhance Sagittarius A star's accretion rate with a lag of roughly 1 year. The G object population will continue making close passages over longer timescales. The dense S-star cluster continuously deposits stellar wind material into the galactic center environment from dozens of nearby massive stars simultaneously. And the galactic center is, on longer timescales, subject to occasional infalls of larger material structures from the surrounding molecular cloud environment. The picture that has emerged from the 2019 megaflare and its aftermath is one of a dynamically complex system where the accretion rate is set by the constantly shifting balance between material supply and the black hole's capacity to process it. Monitoring this system continuously is not a finite project with an expected completion date. It is an ongoing engagement with a living, responsive astrophysical object. The next generation of instruments will bring this engagement to new levels of precision. The extremely large telescope under construction in the Atacama Desert of Chile by the European Southern Observatory will have a primary mirror nearly 40 meters in diameter, the largest optical and near-infrared telescope ever built. Its adaptive optics system will achieve angular resolution several times sharper than current Keck and VLT observations, allowing the positions and brightness of stars far closer to Sagittarius A star than S2 to be tracked with high precision. Stars on tighter orbits, closer to the event horizon, complete their circuits in months rather than years, providing much faster tests of general relativity and much more sensitive probes of the accretion zone. With the extremely large telescope, astronomers will be able to track stars approaching the event horizon closely enough that relativistic effects, gravitational redshift, frame dragging, light bending, become unmistakable signatures in the spectroscopic and astrometric data. The 2019 megaflare has identified the questions most urgently in need of better data. The next decade of instrumentation is being built in part to answer them. The NASA Swift Observatory, designed primarily to detect and study gamma-ray bursts, has contributed to the multi-wavelength galactic center monitoring campaign with its X-ray telescope. Swift's advantage is its flexibility. It can repoint rapidly and accumulate galactic center observations on short timescales in response to alerts from other facilities. When Chandra or XMM Newton detect an elevated flare from the galactic center, Swift can often be scheduled within hours to provide additional X-ray coverage, extending the total observing baseline beyond what any single observatory could achieve. Swift's data from the 2019 observing season showed elevated X-ray activity consistent with the enhanced near-infrared behavior detected at Keck and provided several independent brightness measurements that helped confirm the statistical significance of the enhanced 2019 activity level. The coordination between large observatories with different response times and scheduling constraints is itself a logistical achievement that reflects decades of development in the organization of time-domain astronomical campaigns. the Very Long Baseline Interferometry Program. Monitoring Sagittarius, a star at radio wavelengths continued through the 2019 period and beyond, tracking the position and structure of the compact galactic center radio source at the highest angular resolution achievable from Earth. Radio VLBI monitoring of Sagittarius. A star serves multiple purposes. It constrains the structure and size of the innermost radio-emitting region. It tracks the proper motion of the source across the sky, and it provides an independent baseline for understanding the source's variability properties at low frequencies. During flare events, the radio emission from Sagittarius A star typically brightens on timescales of hours to days, much slower than the near-infrared and X-ray variations, because the radio emission originates from larger radii, where the plasma has had time to expand and cool from the initial energetic event near the ISCO. The radio variability thus traces the outer boundary of the energy release process, encoding information about how energy propagates outward from the innermost accretion zone into the broader galactic center environment. The impact of the 2019 megaflare on the broader astrophysical literature has been substantial. The Tuando et al. Paper has been cited hundreds of times in the years since its publication, spawning follow-up theoretical studies attempting to explain the brightness enhancement through various mechanisms. Magnetic reconnection, driven by fresh material from S2, tidal disruption of an asteroid-sized body, enhanced outflow from a transient jet event, and stochastic variations in the accretion flow amplified by nonlinear plasma instabilities. No single explanation has achieved consensus, and the debate has driven significant advances in theoretical modelling of radiatively inefficient accretion flows and in observational planning for the next generation of galactic center monitoring campaigns. The 2019 megaflare has become a standard reference point in the field, a benchmark event against which theoretical models are tested and whose physical origin motivates ongoing observational effort. In this sense, it has done what the best observational discoveries always do. It has revealed a gap between what we observe and what we understand, and it has made that gap impossible to ignore. The Milky Way's future trajectory includes a gravitational merger with the Andromeda Galaxy, expected in roughly 4.5 billion years. When this merger occurs, the two galaxies' central black holes, Sagittarius A star and Andromeda's roughly 100 million solar mass nucleus, will eventually spiral toward each other over hundreds of millions of years following the merger, ultimately forming a binary black hole system and, after gravitational wave emission removes enough angular momentum from the binary, coalescing into a single larger black hole. The energy released in gravitational waves during this merger will be detectable in principle by future space-based gravitational wave observatories. In the period leading up to the final merger, the perturbation of gas and stars by the infalling Andromeda black hole will dramatically enhance the accretion rate onto both black holes, transforming the merged galaxy's nucleus into what would appear from other galaxies as a luminous active galactic nucleus, potentially hundreds of thousands of times brighter than the 2019 megaflare. The quiet galactic center we observe today is, on billion-year timescales, a temporary state in a longer and more dramatic history. The detection of the 2019 megaflare in real time, as it was happening, represents something historically new. For most of the history of galactic center astronomy, events were discovered in archival data, analysed weeks or months after the photons arrived, without the ability to respond dynamically to trigger multi-wavelength follow-up while the event was still ongoing. Modern alert systems, rapid telescope scheduling, and the global coordination of observational resources have changed this fundamentally for many classes of astrophysical transients. The Vera C. Rubin Observatory, now beginning operations in Chile, will survey the entire accessible sky every few nights, generating a continuous stream of photometric measurements that will detect transient events across the galaxy in real time and trigger automated alerts for follow-up by target of opportunity observation programs. For the Galactic Center specifically, a future mega flare detected at the moment it begins, rather than reconstructed from planned monitoring data, would allow coordinated multi-wavelength campaigns to be assembled while the event is still evolving, providing a far more complete picture of the physical sequence of events than any retrospective analysis can achieve. The 2019 mega flare was caught because monitoring was already underway. The next one will ideally be caught in time to respond. The nature of what science is, at its most fundamental, is illustrated in how the Galactic Center research community responded to the 2019 mega flare. A measurement was made that exceeded expectations. It was documented carefully, checked rigorously, and published with appropriate uncertainty. It stimulated new observations, new theoretical work, and new instrument proposals. It changed the community's prior assumptions about the system's variability range without invalidating the previous framework. The statistical understanding of flare amplitudes was not overturned, it was extended to a higher extreme than previously sampled. The response was not alarm or revision of fundamentals, but the measured expansion of the empirical record and the theoretical models that must explain it. This is how the scientific process works at its best. Not a series of dramatic revolutions that discard all previous knowledge, but an accumulating archive of measurements that progressively narrow the space of viable explanations, each surprising result pulling the theoretical models a little closer to accurate descriptions of physical reality. Sagittarius. A star has a unique role in the history of astronomy that extends beyond its intrinsic physical properties. It was the first supermassive black hole for which the mass was directly measured through stellar dynamics rather than inferred from scaling relations or luminosity arguments. It became the testbed for the S-star orbital measurements that provided the most precise tests of general relativity and the strong field regime outside our solar system. It was the second supermassive black hole to be directly imaged by the Event Horizon Telescope, and in some respects the more challenging target, its successful imaging representing the greatest technical achievement in the collaboration's history. And now the 2019 mega flare has added another chapter to this record. The first time a dramatically unprecedented brightening of a quiescent supermassive black hole was caught in real time, documented with modern multi-wavelength capabilities, and analysed with the full toolkit of contemporary astrophysics. The Galactic Center is not just the nearest example of a supermassive black hole, it is the most thoroughly studied example in human history, and each study reveals something that was not known before. For listeners wondering what the Galactic Center looks like to a hypothetical observer positioned and much closer, say within a few light-years of Sagittarius A star, the answer is both spectacular and terrifying in a quiet way. Within a few light-years of the black hole, the S-star cluster would be visible as a dense swarm of blue hot stars moving at thousands of kilometers per second, their trajectories visibly curved by the black hole's gravity over the span of human observation. The sky background would be blazingly bright by the standards of the solar neighborhood. The stellar density is high enough that the night sky would contain thousands of times more luminosity than the sun provides to Earth. The black hole itself would not be directly visible as a dark region against this background. It would appear, at a few light-years distance, as a region of space where stars are absent and where any gas is glowing in X-ray and infrared wavelengths. During a major flare event, the infrared brightness of the innermost accretion zone would briefly rival or exceed that of the brightest nearby stars. It would be, by any measure, the most dramatic astronomical environment within the Milky Way. What we have learned about Sagittarius. A star through 5 decades of radio, infrared, and X-ray astronomy is not just a collection of measurements about a specific object, it is a demonstration of what is possible. We've looked through 26,000 light years of dust-obscured space through a galaxy arms worth of interstellar medium and pinpointed a region smaller than our solar system where 4 million solar masses have collapsed into a compact region bounded by an event horizon no larger than the orbit of Mercury. We have tracked individual stars through their complete orbits around this object, measuring their positions to within the width of a human hair at galactic center distances. We have detected the light from a single flare, produced in a volume smaller than a light hour, crossing the entire Milky Way to arrive at our instruments on a specific night in May 2019. This is not a story about a distant and abstract universe. It is a story about the power of patient, systematic scientific observation applied over decades to a single, specific, extraordinary object that happens to sit at the center of the galaxy we call home. There is one more scale comparison worth sitting with before the closing thought. Our solar system, the Sun and its planets, orbits the galactic center at a distance of 26,000 light-years, completing one full orbit every approximately 225 million years. This orbital period is sometimes called a cosmic year. In one cosmic year, the Cretaceous period ended, the Chicxulub impactor struck, the non-avian dinosaurs were extinguished, the first mammals diversified into many forms, the first grasses evolved, and primates appeared, developed, walked upright, developed language, built cities, invented telescopes, and detected a single flare from the black hole at the center of the orbit they've been completing for the entire duration of their planetary history. We are somewhere between the orbital position where dinosaurs roamed and the orbital position where telescopes exist. The black hole at the center of that orbit is the gravitational anchor of the whole system, has been there for the entire orbit and for several thousand previous orbits, and it will be there for thousands of orbits yet to come. We are brief travelers on a very long path, and we happen to look up at the center of that path on a remarkable night. The question of danger is the one most commonly posed when news of a galactic center event reaches general audiences. Did the 2019 flare pose any risk to Earth or to life in the solar system? The answer is categorically no, and the arithmetic is straightforward. The total energy released in a major Sagittarius star X-ray flare is roughly 10 to the 42nd ergs, comparable to the energy released by a single supernova. That energy is radiated in all directions equally. At Earth's distance of 26,000 light-years, the energy from the flare is distributed over an enormous spherical surface. The resulting energy flux at Earth's distance is many orders of magnitude below the natural background of X-ray radiation that our galaxy produces continuously from thousands of other sources: pulsars, neutron star binaries, supernova remnants, and diffuse hot gas. Earth's atmosphere provides effective shielding from all of these sources. There is no mechanism by which the 2019 Sagittarius A star flare, or any flare of comparable or moderately greater magnitude, could have any measurable effect on conditions at Earth's surface. Even a hypothetical transformation of Sagittarius A star into a true sustained active galactic nucleus, something the Fermi bubble evidence suggests occurred millions of years ago, would pose minimal risk to Earth from its current position. The most energetic possible concern from a galactic center outburst would be a directed jet of relativistic particles sweeping across the galactic disk. But the geometry of Sagittarius A star's jet axis, inferred from the orientation of the Fermi bubbles above and below the galactic plane, points perpendicular to the galactic disk, roughly north and south relative to the disk's orientation, rather than along the disk itself in Earth's direction. Earth sits in the mid-plane of the galactic disk, roughly 90 degrees away from the jet axis. The radiation from an active accretion state would be intense at close range, but at 26,000 light-years, even the X-ray luminosity of a full quasar reduces to a flux comparable to natural astrophysical sources already present in the sky. The galactic center can produce events of extraordinary scale, while leaving our corner of the galaxy entirely unaffected. What the 2019 megaflare changes is not our safety but our understanding. Before 2019, it was defensible to view Sagittarius A star's variability as the background noise of a genuinely quiet object, modest fluctuations around a roughly constant mean, punctuated only rarely by moderate events. The May 13th megaflare made this picture unsustainable. A source that can produce a 75-fold brightening in near-infrared emission, exceeding all prior records by a factor of several without obvious prior warning, is not adequately described as merely variable around a quiet baseline. It is a source with the genuine capacity for extreme transient events, apparently triggered by the orbital dynamics of its immediate stellar environment. The galactic center black hole is not a dormant relic sitting passively at the gravitational center of the Milky Way. It is a reactive system, sensitive to what comes near it, capable of dramatic responses to relatively modest perturbations in its accretion environment, and embedded in an orbital environment that guarantees continued perturbation for the foreseeable future. There is a subtler scientific lesson embedded in the 2019 detection. Modern systematic monitoring of Sagittarius A covers only about 2 to 3 decades, a tiny sliver of the source's multi-billion-year history. Within that short window, the detection of a single record-breaking event suggests that very large flares may be more frequent than simple extrapolation from the historical average would imply, or it may mean that the recent period has been particularly active by long-term standards, and such events are genuinely rare. Distinguishing between these possibilities requires exactly the kind of long baseline of continuous, well-calibrated monitoring data that is accumulating now. Astronomy is in some ways the slowest of all experimental sciences, testing ideas about processes that operate over millions of years requires patience measured in decades of observational commitment. The 2019 megaflare was caught because astronomers spent 20 years before 2019 building the infrastructure, the expertise, and the archives that made its detection and interpretation possible. The next record-breaking event will be caught because the monitoring continues. The nature of what science is, at its most fundamental, is illustrated in how the Galactic Center research community responded to the 2019 megaflare. A measurement was made that exceeded expectations. It was documented carefully, checked rigorously, and published with appropriate uncertainty. It stimulated new observations, new theoretical work, and new instrument proposals. It changed the community's prior assumptions about the system's variability range without invalidating the previous framework. The statistical understanding of flare amplitudes was not overturned, it was extended to a higher extreme than previously sampled. The response was not alarm or revision of fundamentals, but the measured expansion of the empirical record and the theoretical models that must explain it. This is how the scientific process works at its best. Not a series of dramatic revolutions that discard all previous knowledge, but an accumulating archive of measurements that progressively narrow the space of viable explanations, each surprising result pulling the theoretical models a little closer to accurate descriptions of physical reality. Sagittarius. A star is 40 times larger than our Sun measured by event horizon diameter. It is 10 billion times dimmer than it would be if accreting at full efficiency. It sits at a location that, for Earth, appears in the direction of Sagittarius, low in the southern summer sky. You cannot see it. You cannot see the stars orbiting it, or the accretion disk, or the plasma heated to 1 billion degrees, or the magnetic field lines snapping into new configurations and releasing bursts of near-infrared and X-ray light. All of this is hidden behind 26,000 light-years of space and the dust that fills the galactic disk between us and the centre. What you can see, on a clear summer night far from city lights, is the pale glow of the Milky Way itself, the accumulated light of hundreds of billions of stars, thickest and brightest in the direction of Sagittarius. Somewhere within that glow, behind the dust, sits the most massive compact object in the Milky Way, and it is not as quiet as it looks. The science of the galactic centre has been transformed within a single human lifetime. Carl Jansky detected the radio signal in 1931 without knowing its source. Today we have a direct image of the shadow of the object at the centre of that signal. We have tracked individual stars through complete orbits around it and measured general relativistic effects on those orbits. We have caught the light from a single flare, produced in a region smaller than the Earth-Sun distance, at a distance of 26,000 light-years on the specific night it arrived. The discovery rate has not slowed. Each instrument upgrade, each new observing campaign, each new analysis method reveals something previously beyond our reach. The galactic centre is not a solved problem closed to further surprises. It is a frontier that has been opened wide enough to see its true complexity, but not yet thoroughly enough to fully map it. The black hole at the centre of our galaxy has been there far longer than the solar system has existed. It will be there long after the Sun has exhausted its hydrogen and expanded into a red giant. The stars of the S-star cluster will continue their tight, fast orbits. S2 will return to periapsis in 2034 and deposit another increment of stellar wind material into the accretion zone. The G objects will make their slow passages. The molecular clouds will continue recording the echoes of past outbursts in their fluorescent X-ray glow. And Sagittarius A star will do what it has always done, exist at the gravitational heart of 400 billion stars, processing the trickle of material that makes its way inward, releasing occasional bursts of energy that will travel 26,000 years before anyone detects them. The 2019 megaflare was one such burst, an extreme one, an unprecedented one, but not the last. The galactic centre is the most powerful laboratory for testing general relativity in the strong field regime accessible from Earth. The orbits of S2 and its companion S stars have now provided measurements of the gravitational redshift, the Schwarzschild precession, and the frame-dragging correction to orbital dynamics that were previously undetectable in any other astrophysical system outside our solar system. The 2018 S2 periapsis, captured in unprecedented detail by the gravity instrument, yielded the first direct detection of Schwarzschild precession around a massive black hole and placed constraints on hypothetical modifications to general relativity that are among the strongest available in the strong field regime. Each future S2 periapsis, and each periapsis of the other S stars with shorter orbital periods, will provide additional tests with increasing precision as instrument capabilities improve. The galactic centre is simultaneously the most challenging astronomical target to observe and the most productive arena for testing the theory that underlies all modern astrophysics. The magnetic field of the galactic centre extends far beyond the immediate vicinity of Sagittarius A star. Radio observations have detected a population of filamentary structures called non-thermal radiofilaments that extend perpendicular to the galactic plane for distances of tens of light years in the inner few hundred light-years of the galaxy. These filaments are thought to trace strong, ordered magnetic field lines threading the diffuse ionized gas of the galactic center region. The magnetic field implied by these filaments, roughly 1 milligauss over large volumes, is far stronger than typical interstellar magnetic fields in the outer galaxy, and represents a substantial reservoir of magnetic energy stored in the galactic center environment. This large-scale ordered field provides a background context within which the much stronger, tangled fields near the innermost accretion zone of Sagittarius A star operate. How the two scales of magnetic field structure interact, whether the large-scale field is continuously regenerated by dynamo processes near the black hole, or whether the connection is more indirect, remains an open question of galactic center astrophysics. Supermassive black holes like Sagittarius. A star are now understood to play a fundamental role in the evolution of their host galaxies, not just as passive consequences of galaxy formation, but as active participants in regulating it. When a black hole at the center of a galaxy undergoes a period of high accretion, the energy it releases can heat the surrounding gas, drive powerful winds, suppress star formation, and in extreme cases expel material from the galaxy altogether. This feedback between the central black hole and the host galaxy, called a GN feedback, is now considered an essential ingredient in understanding why massive galaxies stop forming stars while less massive galaxies continue. The Fermi bubbles are a direct piece of evidence that Sagittarius A star has exercised this feedback function in the Milky Way's recent past. The relatively small size of our galaxy's central stellar bulge, compared to the predictions of models that emit AGN feedback, suggests that past activity from Sagittarius A star has helped shape the large-scale structure of the Milky Way itself. Stepping back from the specific details of the 2019 mega flare, there is something worth acknowledging about the broader achievement it represents. 3 generations of astronomers working across 5 decades built the conceptual framework, the observational infrastructure, and the analytical tools that made the detection and interpretation of May 13, 2019 possible. Carl Jansky's 1931 radio detection, the 1974 Bialik-Brown compact source identification, the 1990s S-star tracking programs at Keck and the Very Large Telescope, the 2001 Chandra X-ray flare discovery, the gravity instrument commissioning in the 2010s, Tuando's monitoring run in May 2019, each step built on the previous one, each generation of astronomers inheriting a richer knowledge base and a more powerful instrumental toolkit than those who came before. The 2019 mega flare was not the result of a sudden breakthrough. It was the product of continuous, patient, cumulative scientific work over nearly a century. That is what makes it not just a discovery about Sagittarius A star, but a demonstration of what sustained scientific commitment can achieve. Returning to the question of how rare the 2019 megaflare was, a precise statistical characterization is difficult because the historical record of systematic near-infrared monitoring spans only about 20 to 25 years. If flare amplitude follows a power law distribution with the slope measured from the moderate amplitude events that are well sampled in that record, a flare 75 times the typical brightness might be expected to occur roughly once per decade to once per century, depending on the exact slope of the distribution. The fact that one occurred in 25 years of monitoring is not in strong tension with the once per decade estimate and would only become unexpectedly frequent if multiple such events had been observed. Alternatively, if the 2019 flare represents a qualitatively different physical mechanism, triggered specifically by the S2 periapsis, rather than arising from the stochastic background accretion variability, then its recurrence time is not set by the power law distribution of normal flares but by the orbital period of S2, and the probability that each periapsis produces a similar accretion enhancement. Disentangling these two possibilities is one of the central empirical goals of the ongoing monitoring campaign. Quantifying the change in accretion rate implied by the 2019 megaflare requires converting the observed luminosity enhancement into a physical accretion rate. This conversion depends on the assumed radiative efficiency of the accretion process, which in Sagittarius A star's advection-dominated flow is inherently low, perhaps 0.1% of the rest. Mass energy of the accreting material is converted to radiation, compared to 10 to 40% for a thin disk around a more actively accreting black hole. Given this low efficiency, the factor of 75 increase in near-infrared luminosity during the 2019 megaflare corresponds to a transient increase in the effective accretion rate near the innermost stable circular orbit by something on the order of 100 to 1000 times the quiescent baseline rate. In absolute terms, this enhanced rate is still far below what would be needed to sustain even a mild active galactic nucleus. But on the timescale of the flare, minutes to hours, the innermost accretion zone was processing material at a rate thousands of times higher than its long-term average, channeling that material's gravitational energy into radiation with a transient efficiency dramatically higher than the quiescent mode. The energy of the 2019 megaflare, while extraordinary in the context of recent Sagittarius A star observations, is dwarfed by other energetic phenomena in our galaxy. A typical supernova releases approximately 10 to the 44th ergs of energy in all forms, of which roughly 1% escapes as visible and X-ray light. A magnetoflare, the most energetic transient event known to occur within the Milky Way, can release as much as 10 to the 46th ergs in a fraction of a second from a neutron star with a magnetic field trillions of times stronger than the Sun's. On December 27, 2004, a magnetar in our galaxy designated SGR 1806-20 released a giant flare that, for 0.2 of a second, was brighter in gamma rays than all other celestial sources combined, including the full moon. The Sagittarius A star mega flare, while remarkable, exists on a lower rung of this energy hierarchy. What makes it notable is not its absolute energy, but its origin. A supermassive black hole that is nearly dormant by the standards of its class, producing a transient brightening that briefly illuminates the galactic center against its usual near darkness. The drama is in the contrast, not the absolute scale. Our Milky Way is not unusual in having a quiescent central black hole. Surveys of nearby galaxies have found that supermassive black holes in the centers of most large, old, elliptical and spiral galaxies are similarly underluminous relative to their mass. Active galactic nuclei, black holes that are brightly and continuously accreting, were far more common in the early universe, when the supply of gas available to fuel them was much greater. As galaxies aged, used up their gas in star formation, and saw their central regions cleared by AGN feedback itself, the supply of material to their central black holes diminished. The result in the present-day universe is a population of massive galaxies whose central black holes have the mass fingerprints of past high accretion activity, but are currently operating at low rates. Sagittarius. A star is one of the most extreme examples of this pattern, extraordinarily massive for the level of current activity, but it is part of a broad class. Understanding what occasionally disturbs these quiescent black holes, triggering mega flares or longer episodes of enhanced activity, is one of the central questions in the field of low-luminosity active galactic nuclei research. The energy released during the May 2019 megaflare did not simply vanish after the peak. Some of it was radiated as near-infrared and X-ray photons that have been travelling outward through the galaxy for more than 6 years since the event was detected. was deposited as heat into the surrounding plasma, raising the temperature of the gas in the immediate vicinity of the flaring region and driving a mild pressure-driven outflow that will slowly mix with the broader galactic center medium over months to years. Some may have gone into accelerating a mild relativistic outflow or jet that carries energy mechanically into the galactic center environment. The partitioning of the total energy release between radiation heat and mechanical outflow is one of the quantities that current models seek to constrain, because it determines how efficiently a black hole flare can influence the surrounding gas, whether flares contribute meaningfully to the overall energy budget of the galactic center region, or whether their energy is simply radiated away and lost to the local environment without lasting dynamical consequence. Making the physics of the 2019 megaflare tangible requires analogies that bridge the gap between everyday experience and the extreme conditions near a supermassive black hole. Magnetic reconnection releases energy stored in magnetic fields the way a stretched rubber band releases energy when it snaps. The acceleration of electrons to near light speeds by the reconnection event is analogous to a particle accelerator, except that the electromagnetic fields near a black hole are billions of times stronger than anything human technology can produce. The temperature of 1 billion degrees Kelvin in the flaring plasma is approximately 70,000 times hotter than the surface of the Sun, and the total energy released in the flare, equivalent to millions of suns burning simultaneously, came from a volume smaller than the distance between Earth and the Sun, in a time shorter than the duration of a long movie. No analogy adequately captures the combination of energy, temperature, density, and spatial compactness that characterizes the innermost region of a supermassive black hole during a major flare. The mathematics is exact, the intuition fails, and that failure of intuition is, in its own way, one of the most honest things that physics can tell us. The accumulation of knowledge about Sagittarius. A star over 5 decades reflects a quality that is easy to underestimate in science: patience. Not every observing campaign produces a major discovery. Most nights of galactic center monitoring produce data that fills in the statistical picture slowly and incrementally, extending the temporal baseline, improving the calibration of the instrumental response, catching moderate flares that constrain the lower end of the amplitude distribution. The astronomers who designed the monitoring programs in the 1990s did not know that a mega flare would be detected in 2019. They built the infrastructure because systematic monitoring of the galactic center was scientifically important, and because the accumulation of data over long baselines was the only reliable way to understand the source's true behavior. The 2019 megaflare was the reward for that long investment, but it was not the only reward. Everything that had been learned about Sagittarius. A star's normal behavior in the preceding 20 years was the context that made the 2019 deviation recognizable and interpretable. Without the baseline, the extraordinary would be indistinguishable from the ordinary. The 2019 megaflare attracted significant public attention when Twando's findings were published. The story resonated beyond scientific circles because its core elements are universally accessible. A black hole at the center of our galaxy, quiet for decades, suddenly releasing a burst of energy orders of magnitude beyond its normal output. The language of the title, brighter than 10 million suns, translates abstract astrophysics into something that can be grasped without a physics degree. This accessibility matters. Public understanding of and support for fundamental science rests, in part, on the ability of scientists to communicate discoveries in terms that connect with general human curiosity. The galactic center, with its extreme physics and its role as the gravitational anchor of our home galaxy, is one of the most compelling objects in astronomy for exactly this reason. It is close enough to be ours, part of our galaxy, our galactic neighborhood, and remote enough to be genuinely alien. When it does something remarkable, the story belongs equally to specialists who can interpret the data and to anyone who has ever looked up at the Milky Way on a clear night and wondered what lies at the centre of that diffuse band of light. We are living at a moment in the history of galactic centre astronomy that future generations may look back on as foundational. Within a span of roughly 30 years, we went from having only statistical evidence for a massive compact object at the galactic centre to having a direct image of its shadow, a catalogue of dozens of stars in resolved orbits around it, a measurement of general relativistic effects on those orbits, a record of its X-ray and infrared flaring behaviour, a direct image of the hotspot orbiting near its innermost stable circular orbit, and the detection of an unprecedented mega flare that briefly illuminated the galactic centre more brightly than anything previously recorded in the modern observational era. The next 30 years will bring instruments of far greater power, and the knowledge accumulated in those 30 years will likely make our current understanding look correspondingly incomplete, the way our current understanding makes the knowledge of the 1990s look incomplete. We are not at the end of the story of Sagittarius A star. We are, if anything, close to the beginning of the phase in which we have the tools to understand it properly. There is a private quality to looking up at the Milky Way on a dark, clear night that no photograph can fully replicate. The band of light extends across the sky in a way that is simultaneously vast and intimate. Vast because it spans from horizon to horizon, encompassing a volume of space that the human mind cannot genuinely comprehend. And intimate because it is our home, the galaxy in which every human who has ever lived was born and will die. At the thickest, brightest part of that band, roughly in the direction of Sagittarius, low in the summer sky from the northern hemisphere, lies the galactic centre, 26,000 light years away, hidden behind dust, invisible to the eye, but known, measured, understood in outline if not yet in full detail. The Milky Way that arches overhead on a summer night contains, somewhere within its brightness, the location of a 4 million solar mass black hole that occasionally releases events brighter than 10 million suns. That knowledge belongs to us now. It is part of what it means to be alive at this moment in the history of understanding the universe. As the universe continues its ancient operations, the galactic centre goes about its business with no awareness of being observed. The S2 star is, at this moment, somewhere on its 16-year orbit around Sagittarius A star, its surface blazing at 30,000 degrees, its stellar wind streaming outward at thousands of kilometers per second, some fraction of that wind bending toward the black hole's gravitational well. The other S-stars are on their own orbits, moving at hundreds to thousands of kilometers per second, tracing the ellipses that have been recording their positions in the data archives of observatories on Earth for 30 years. Sagittarius. A star is, right now, probably in a relatively quiet state, fluctuating modestly in brightness, processing the steady trickle of material that makes its way inward, releasing occasional small flares that nobody on Earth is catching because the galactic centre is currently on the other side of the sky from the observatories scheduled tonight. This is fine. The record is being built, the monitoring continues, and the universe does not require our attention to proceed. The scale of what we have discussed tonight is best processed not with urgency, but with stillness. 26,000 light years, 4 million solar masses, a burst of energy brighter than 10 million suns, released in a volume smaller than the Earth-Sun distance, from a flare that began and ended before anyone alive today was born. These are facts. They are measured and verified, and as solid as the science that produced them, and they are entirely compatible with sitting quietly, breathing slowly, letting the mind rest. The universe does not require us to be anxious about its scale. It requires nothing of us at all. We are the only part of it that asks questions about it, and asking those questions has revealed things that are genuinely extraordinary. The black hole at the center of our galaxy has been doing what black holes do for billions of years. It will continue when we are asleep. There is something deeply restful in that. The universe is vast and ancient and patient, and it does not need our participation to continue. We are, for this brief moment, simply watching. The scientific response to the 2019 mega flare set in motion, observing campaigns that have continued in the years since. The 2022 Event Horizon, telescope image of Sagittarius, a star the direct image of the black hole shadow itself, was conceived and executed independently of the 2019 flare, but its release in May 2022 deepened the interpretive framework for understanding events like it. Combining the shadow geometry from the EHT image with the orbital parameters of the S2 star and the statistical properties of the flare record allows theorists to construct increasingly constrained models of the accretion geometry near the innermost stable circular orbit. Future EHT campaigns with additional telescopes and extended baselines will improve the angular resolution and dynamic range of those images. The next S2 periapsis, expected around 2034, is already being planned as a coordinated multi-wavelength observing event. The 2019 megaflare is therefore not a conclusion but a reference point, a fixed marker against which future activity will be compared, interpreted, and ultimately understood within a theoretical framework that does not yet fully exist but is being assembled, observation by observation, with every monitoring epoch. There is a question that the 2019 megaflare raised and has not yet answered. Was it the largest flare that Sagittarius A star will produce in the foreseeable future, or a hint of something still more energetic to come? The observational record extends back only about 25 years, and the power law distribution of flare amplitudes, if it holds over the full range, implies that events 10 times more energetic than the 2019 event should occur, just rarely, perhaps on timescales of centuries. A Sagittarius, a star mega flare 10 times more energetic than the 2019 event, would briefly illuminate the galactic center at the luminosity of 100 million suns. Its echoes would propagate through the surrounding molecular clouds and be detectable long after the flare itself subsided. It would be detectable across the galaxy and in external galaxies with sufficiently sensitive telescopes. The possibility that we are in a relatively quiet interval between such events, that the 2019 megaflare was not a maximum but a threshold, is one of the more humbling implications of the flare statistics, and a reminder that the history of Sagittarius, a star we have access to, is a brief excerpt from a far longer record that the universe has not preserved for us in any accessible form. The flare detected on May 13, 2019 has long since faded. The near-infrared brightness of Sagittarius, a star, has moderated from its extraordinary peak. The accretion region has returned to a somewhat elevated but sub-spectacular state. The light from the peak moment of the flare is now more than 6 light-years from where it originated, travelling outward in all directions at 300,000 kilometers per second, crossing through interstellar space, weakening with the square of the distance, heading eventually toward the vast emptiness between galaxies where no telescope will ever receive it. The plasma that generated it has since cooled. The electrons that emitted it have lost their energy to radiation and are no longer relativistic. The magnetic field has relaxed into a new configuration. Behind all of it, at the center of the Milky Way, the black hole continues its ancient, patient work, the same work it was doing before the 2019 event, and before the 2018 S2 periapsis, and before the Fermi bubble outburst, and before the first stars in our galaxy formed. What the 2019 mega flare gave us was clarity. It showed that our galactic center is a more reactive and dynamic system than the preceding years of relatively quiet monitoring had suggested. It demonstrated that specific orbital events, a star's close passage, the infall of disrupted material, can trigger accretion responses far beyond the statistical norm. It deepened the connection between the physics of the black hole and the orbital dynamics of the stars and gas around it, showing that these are not separate stories, but one coupled system. And it provided the Galactic Center research community with a compelling specific target for continued observation, a reason to keep watching, to build better instruments, to design new campaigns, and to be present and ready when the next extreme event arrives. That event could occur at any time. It could be happening right now. Its light somewhere between the Galactic Center and us, 26,000 years into its journey, expected to arrive at no particular moment that anyone can predict. Let that thought settle as you rest. Somewhere in the direction of Sagittarius, visible on a summer night as the thickest part of the Milky Way, low in the southern sky, a black hole 4 million times the mass of our Sun sits at the center of our galaxy. It has been there longer than the Earth has existed. Every star you can see on a clear night, and 400 billion more invisible to unaided eyes, orbits it. The light you see from the Milky Way tonight left its sources hundreds to thousands of years ago. The flare observed in 2019 originated before the last ice age ended, and the universe will continue producing such events long after every living thing currently on Earth has completed its brief passage through time. There is nothing threatening in this. There is only scale, extraordinary, patient, ancient scale. The black hole at the center of our galaxy is not a hazard. It is a fundamental feature of the system we inhabit. Knowing it is there, knowing its mass and distance and history and capacity for sudden brilliance, is one of the small and remarkable things that makes this particular moment worth having been awake for. Sleep well beneath the Milky Way. Its center has been doing this for a very long time.